Okay, so good morning. So we were looking at SPN network, the block cipher, substitution permutation network, and I promise you to, I will show you how to actually decrypt, how to plan an attack, or how to mount an attack on SPN. And I think we have done some preparation for that uh, in the last class. Today, few more things are required before we can actually mount an attack, and so I'm going to cover that, and then we'll actually show you how we can guess the key. So again, recalling most of the stuff. So we are looking at block cipher, which is a kind of a iterated cipher, and it is a sequence of permutation and substitution operations. So there are a bunch of round keys and the key schedule. Key schedule is generated from a random unknown key. I mean, random from a random key, which can give you the scheduled keys like K1, K2, Kn, which are used at each round. Okay. So we start with a plain text and we assume that it's a binary string, right? Binary sequence of length L into M. Okay, and then we have, this is our process from plain text to ciphertext using these kind of round operations that we do. And there is a inverse of it, right? So that from the given ciphertext, you can get the plain text back. Okay. So the two main components of substitution and permutation. One is substitution. So we take L bits and substitute with some other bits, L bits. Okay. That is done by this S box, this function. And permutation, all LM bits are changed in certain order. So some permutation is applied to those bits, you know. So these are the two important components of substitution permutation network. And then we talked about, so here is our whole operation of encryption, how it works, right? And I have shown you one example. Well, n is equal to m is equal to n is equal to 4, and our two functions. One is the substitution. So we talked about hexadecimal numbers. So these are the 16 numbers from 0 to 9, and then A to F. Each one is 4-bit. Okay. So this pi s is basically substitution of these bits, right? So these 4 bits you're, substituting with respect to this order. Okay. And then there is a permutation of all bits, in some order. So we apply this permutation, 16 bits, we get these 16 bits, this permutation is applied. And we talked about, in this example, there are 16 such S boxes, like S11, S21. So starting with the plain text, then there is a key, first scheduled key, K1, then these boxes, S11, S21, S31, S41, then there is a permutation of bits, then again the key is added, then again substitution, then again, okay, permutation, and then keys are added. Like that, we have these many things. So starting from the plain text, we are getting the ciphertext. Okay. Okay. What are you discussing? Right. Yes. So, okay. So starting from plain text, we are getting the ciphertext with these operations. And implementation of these networks are very simple. Basically, you can just use, uh, a lookup table, and memory requirement is also less. L times 2 is for L bits actually. Okay. I've shown you how to generate key from a given key, random key. Basically, it's a random key. And from random key, we are getting scheduled keys, sub keys, K1, K2, K3, K4. Okay. And we are getting so from the plain text, we can get we can apply this and we get this kind of things. So all these things are clear. You know, we talked about these things last time. Now, again, I'm recalling what were the attack process. We talked about biasness, you know, if you remember. So we treat each of these, you know, bits as a random variable, right? So our linear cryptanalysis attack, what we are looking at, suppose it is possible, it's talking. Anyway, suppose it is possible to find a probabilistic relationship, linear relationship between a subset of plain text bits and a subset of state bits. So those WRs are state bits, if you remember, at RS round. Okay. So in other words, there exists a subset of bits where exclusive OR behaves in a non-random fashion. So it takes on the value 0, say, with probability bounded away from half. As I mentioned, this is a tedious, lengthy process, so please pay attention because, you know, you will see that there were so many steps involved. And this was discovered by Shamir and his colleague, you know. So it's really very, very important thing. Okay. So in the attack, we assume that attacker has a large number of plain text and ciphertext pairs. So all encrypted with the same unknown key. I will show you for this example. We take about 8,000 such pairs, and we do the calculations. Okay. So that's why it is known as known plain text attack. Okay. For each of the pair, we will begin to decrypt the ciphertext using all possible candidate keys. For the last round of the cipher, for each CK, we compute the values of the relevant state bits involved in the linear relationship and determine if the relationship holds. Okay. So if it holds, sometime it may not hold. When it does, we increment a counter. Okay. So at end of the process, we hope that the candidate key that has a frequency count further away from half. So, you know, then this is the number of plain text, ciphertext, that text pair, we get the correct values for the sub keys, you know. So I think I'll show you with examples how we can do this. So I think we last time covered the piling lemma. Okay, so assuming that probability of xi bar is equal to 0 is pi, probability of xi bar 1 is equal to 1 is 1 minus pi, and we assume that these variables are independent, you know, random variables. We have done these calculations, and important thing that we describe biasness of a random variable xi is epsilon I, which is pi minus half. Okay, where each random variable xi has probability xi, you know, xi has a probability pi. Okay, so this value lies between minus half and half, and so then we are considering these kind of expressions, xi1 plus xi2 plus xik, and you know, for this kind of random variable, we are looking at the biasness of this random variable. Okay, and we found this following formula, right? This epsilon I1 I2 ik is equal to 2 raised to power k minus 1 times partial product j is equal to 1 to k epsilon ij. So this much we need to remember. Now, I mean, of course, we have done the proof by induction last time. Now we proceed further. Now we require few more things. Okay, so now we are ready. Linear approximation of S boxes. Now what we are going to do, we are going to do the linear approximation of the S boxes. So these are the S boxes are these substitutions. So from 0 1 m to 0 1 n. Now suppose x is equal to x1 x2 xm is a vector uniformly it's a uniform randomly chosen, right? Now from 0 1 m, each coordinate defines a random variable xi bar. So if I look at any entry here as a xi, small xi, each coordinate defines a random variable xi bar. Okay, and having taking on the value 0 or 1 and having bias epsilon I is equal to 0 for that particular random variable. We have bias epsilon I is equal to 0. Then y is equal to y1, y2, yn is the output. Each coordinate of yj defines random variable yj bar. Then we can compute. So basically, these are the observations. The probability that x1 bar is equal to x1, x2 bar is equal to x2, xm bar is equal to xm, little xm, y1 bar is equal to y1, y2 bar is equal to y2, and so on. Yn bar is equal to yn. This probability is 0 if for this input x1, x2, xm, image under pi s is not equal to the output. So output is y1, y2, yn, right? If this is not there, then this probability is 0. And this probability turns out to be 2 raised to power minus m if this is actually an image. Okay. So this is a observation. Now we look at the bias of this basically, something like xi1 bar plus xi2 bar dot 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 xit bar plus yj1 bar plus yj2 bar plus dot 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 yjl bar, right? This is our expression. We are looking at the biases of this. So attack can be mounted when above form has bias that is bounded away from 0. So if this kind of expression has bias bounded away from 0, then attack can be mounted. Okay. Now again, we look at the small example. Our example that we are looking at, L is equal to M is equal to 4. So we are looking at these 4 variables here and 4 variables there. So basically, how many possibilities are there? Each has 4 choices. I mean, each has, how many choices? We have these many choices, right? How many vectors are there? You can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 vectors are all 16 possibilities. So we have x1, x2, x3, x4 as a input and y1, y2, y3, y4 as a output. So these are the random variables defined by the S box. Okay, all possibilities I have written. Now I will show you how to use this table actually. Now if you look at this expression, x1 bar plus x4 bar plus y2 bar, okay, and I look at basically when this probability of x1 bar plus x4 bar plus y2 bar is 0. So I can go actually, x1 bar, x4 bar and y2 bar. Go here when this could be 0. X1 bar here, x4 bar and y2 bar, right? And we can count how many times this is 0, right? The sum is 0. How many times by looking at all the pairs, I can observe that. Actually, it turns out that, so this probability is equal to number of rows in the table, which are giving you this. There are 8 values divided by total 16 values. So this probability is half. So biasness of this random variable is, basically 0, because when probability is half, biasness you can compute half minus epsilon I, right? So this value is 0. Okay. I'm just giving you an example how to look at the table. Okay. So similarly, as an exercise, you can compute bias of this, and it turns out that this is minus 3 by 8. So I leave it as a verification for you. You say that when this will be 0. So you need to look at in the table when, for what are the possibilities when this will give you 0, right? So now there are 2 raised to power 8, 256 possible random variables. We can actually do these calculations. So in general, our expression is, so there are input random variables, So, we have a most general expression is something like this: summation I is equal to 1 to 4, where ai xi bar plus bi yi bar. Now these ai's and bi's are 0 or 1. So basically I can expand it. So values are a1, a2, a3, a4. Here the values are b1, b2, b3, b4. These are the important things. Rest of all are, so it's like a compact notation. And now these 4 bits we can convert into hexadecimal. So we have input sum and output sum. We can write down in the hexadecimal. For example, if we have an expression something like this: x1 XOR x4 bar plus y2 bar. So you see that x1 is present 1, x2 is not there, x3 is not there, x4 is present. So this is 1 0 0 1 vector. Okay. Similarly, y2 bar, so y1 is not there, y2 is there, y3 is not there, y4 is not there. So 0, 1, 0, 0 is correspond to this value, right? So essentially we have, this will have hexadecimal value 9 and this will have hexadecimal value 4. So the whole expression can be written in the hexadecimal numbers, which is a compact notation for us. Okay, so this whole expression is 9, 4. Input variables and output variables, right? Okay, this is something easy to observe. Now, for a random variable, basically input sum we call it as A is equal to A1, A2, A3, A4, and output sum B is equal to B1, B2, B3, B4. If we define NLAB as the number of binary A tuples x1, x2, x3, x4, y1, y2, y3, y4, such that output is image of x1, x2, x3, 4 under pi s. Okay, so then we can compute this also actually, right? So you can see that for NL94 in our previous example here, this is 9 comma 4, right? So this is 9 comma 4, we can compute NL 9 comma 4 is 8 actually. Okay, and then so we can compute what is epsilon and 9 comma 4, which is 0, right? So basically the biasness of the random variable having input sum as A and the output sum B is defined as NLAB minus 8 divided by 16. Okay, this is the total biasness of these kind of expressions in general. So when you put NL and 9 comma 4 is equal to 8, we know this value is 0. So these are the total table for NLAB. You can compute for all possibles 16 possibilities for A and 16 possibilities for B in the hexadecimal form, and we can compute these values. So this is known as linear approximation table. Now we look at the you see, now we need to pay little attention here. This is the linear approximation of the substitution permutation network. So out of 16 boxes, so right now we are saying there is one box S21, another box S22, another box S23, and one box S43. These 4 boxes are there which are used for the linear approximation. And then we'll try to compute these random variables, biasness of these random variables. So what we do, so basically how do we read this first of all? U1, so you can see that X is the plain text. Okay. Then we have, this K1 is our, key thing. U1 is the input to, so if you look at just focus on S21, actually I am just saying that we now focus on anyway, I think I don't have the pen here anyway. So I'm saying that we just focus on this S21 here. See that what is this variable? U1 is the round 1. So whenever is the subscript, that means round 1. So round 1 and which bit? 1, 2, 3, 4, 5th. So this is the 5th bit. Okay. So we are looking at AU51. This is our this bit, which is having an arrow, and there is nothing here. Then this is 5th, 6th, 7, and 8th. So 7 and 8 is also there. Okay. This is the input. So so variable U is the input. Subscript is the round, which round the input is. Okay. And subscript denotes the bit number. So this is U51 plus U71 plus U81. Okay. Got it? And then this is the S box. And what is the output of a S box? You see, which bit is coming? So basically, I am just saying in general, UIR is the input of the S box and VIR is the output of the X box. R denotes the round in which you are. Round 1, round 2, round 3, round 4. And I denotes the bit number. Okay? In both either UI, which is input, or VI as the output. So what is coming as the output from there? 1, 2, 3, 4, 5th bit. 5th bit is coming as the output from the S2 1, right? So we 6, right? Yeah, 6. 1, 2, 3, 4, 5, 6. 6 bit is coming. So you see, I'm just computing a random variable T1 bar for the S21 box, which is U51 plus U71 plus U81 plus V61. Okay, this is our T1, and we can compute the bias again using those lemmas. Turns out to be 1 by 4. Then we go to the next S box, which is S22. So S22, so 1, 2, 3, 4, 5, 6 is going inside, right? U62 in the round 2. U62 plus, which one is there? Output. What is the output from S22? So one input, and there are two output. One is this, another one is this. What are those bits? This one is 6, right? And the other one is 8. So basically, for S22, we compute the whole random variable. It is U62 plus V62 plus V82, and you can compute that whole biasness is minus 1 by 4. Then we go to this one, S23. So S23, you can see that input bit is this, and output bit is this, and this, right? So what we can again compute, and for this one, this is the input, and output is this and this, right? These two. So I can just compute everything like that. So T3 is U63 plus V63 plus V83. Then you compute the biasness, which turns out to be minus 1 by 4. And for T4, for the fourth one, we have this is the expression. By observing the picture, you can compute, and then you can compute what is the biasness, right? So basically, we have all the 4 variables here, okay? Then I can sum all of them, and I can look at the biasness of the whole thing using piling lemma. This turns out to be minus 1 by 32. Okay, using piling lemma, I'm just computed. So 2 cube, all those formula we apply, and we get this value here, right? So you see, so many things are involved here. By the way, you can see there's so much tedious, so just trying to break the key, so much analysis is done. This is done by Shamir, Shamir is a very famous cryptographer. These Israeli people are very great people, actually, You do all good things, okay? So then you see that, then I can actually do some sort of recalculations. For T1, you observed we have got this thing. Now using the values in the pictures, right, I can actually simplify the expressions by using input bits and the key bits, because those are also involved there, right? So just by observing a picture, I can simplify T1 bar is this, T2 bar is this, T3 bar is this, and T4 bar is this, all this simplification by just look. So now we involve input bit and key bit as well, So the overall thing will be, so when we sum everything, we get something like this. Okay, and we just saw. So still, you see, there are. You remember, U6 is the input and V6 is the output. We can further simplify, the whole thing. And we know that this has bias minus 1 by 32, which we just computed using piling lemma. So we can again substitute these values, and we simplify here further. We get something like this. So now you see that we have value in terms of plain text, x5, x7, x8 bit is involved in the plain text. Then input U64 is input to which? Round 4, right? Round 4, 6 bit. Input, so next one, so everything is there. And rest of the key things I have written here. So, now this expression, all this, okay, again, you see so many things. If these keys are either 0 or 1, the whole thing simplifies to this. These are all keys. So keys are, we are separating it out. Rest of the plain text and the bits are other expressions. So now we are looking at this expression. We call it as 4.3, which is other than the key stuff, So again, one can check that this has biasness plus minus 1 by 32. Okay, and so basically, No, no, sign depends on the table value of used key basically so now we arrived here. Okay. So this is a, again you see that we are just doing a small example, and only small things I'm showing you how it will work. And I think I've shared one document with you. You can see that yesterday in details how these things happen. So this is the whole expression. So now the whole thing is this 4.3 actually has bias bounded away from 0. So since it is having biases bounded away from 0, we can actually carry out a linear attack. Now we start the attack. How we'll do? So basically, T is the total number of plain text and ciphertext pairs. So they are roughly, we take around 8,000 such pairs, and tau is the collection of such pairs. Okay. The attack will allow us to obtain the 8 key bits in K51 and K54. So basically, these are the bits. K55, K65, K75. This is all round 5. Okay. We try to guess round 5 key bits. Okay. So XOR of the output of the sub keys. Okay. So then basically these 8 bits. So you see, remember the approach what was there? There are 2 raised power 8. So there are 8 bits. So 2 raised power 8 possible, for the list of 8 key bits. So we try different candidate keys. So if you can think of it like 8 tuples, and we are trying one by one, right? So for each x comma y, and for each candidate key, sub key, it is possible to compute a partial decryption of y and obtain the resulting values for the this the fourth round input. Okay, this is how actually I will show you the algorithm now. So basically, then we compute this expression because these two things are obtained. Now we maintain a array of code words, array of counters, with 256 possible candidate subkeys, and increment the counter corresponding to a plain text subkey where where 4.4 this expression has value 0. At the end of the counting process, counter so basically you will see that the counter has value close to t by 2. T is the number of pairs. In this case, it is 8,000. And but for the correct subkey, this value is t by 2 plus minus t by 32. Okay, so that is how we obtain the values of the keys. So I think it is a kind of project. I think I've given you a project, and this is the general algorithm now. Basically, how we use it. L1 and L2 are the hexadecimal numbers in this thing. Okay, tau is the pair, tau is the collection of pair, t is the total number of pairs, and pi inverse we are trying to just find out, right? So the whole algorithm, I think you can just see. Finally, output is most likely 8 subkeys bits we can guess actually out of this process. So again, one has to go over it. So I think that's why, if you remember, the first link that I provided to you, there is a class project actually, right? Just given to decrypt one. I mean, so S-box approximation process. It's a very lengthy process, right? It's not very straightforward thing. That's why So I'll request you, see if you can really do this process. It's very tedious, right? It will take a couple of days for you to actually figure out the subkeys. But the good thing is that actually it works. Okay, and I think we have assumed at one place that these random variables are independent. Actually, it is not, but it works. Okay, so that assumption is also there at one place. So what I'm saying that this is really very tedious process. That's why I would say that just try, if you can try to decrypt it. So this will be a really nice thing. But anyway, it's something which is useful, and it works actually. Anyway, so this is all about linear approximation. Differential cryptanalysis we will not do. No, it is right now. So anyway, this is all about, as I mentioned by Shamir. So you got the whole thing. We need to compute biasness of the random variables, right? Of those kind of expressions. For that, we use piling lemma. When do the linear approximation, we look at, these kind of tables, try to guess the keys. So final algorithm is this actually. So even if you want to actually break it, I mean, you have to do a lot of calculations really. Okay. So I hope you enjoyed the Undhio, right? So that's all, I guess. I'm not going to pick up any other one. That's all.